So for the next several days, from now through next Tuesday, I think Tuesday is going to be an odd day with an early release. I think we'll have class today, we'll have 45-minute all day on Monday where I'll see you, and then we'll see each other for about an hour, 15 minutes, I think, maybe just an hour on Tuesday. But we're working on these 4 things, right? And what I had asked you to do on Tuesday, ideally was get through the process of making those free body diagrams and kind of setting up at least an idea. You didn't necessarily have to collect data, although ideally some of you would have, but at least get something set up so that you could make a measurement of the amount of friction that was acting on your car. And then there's these 2 pieces here, which most of you will hit next week, because most of you are going to take today to kind of come up with your predictions, and then next week we'll be doing the testing. When I say how well can you work with free body diagrams, or how well can you use static and kinetic friction with Newton's second law, what I mean by that is not, do you have the right answer written on your paper, but given any scenario, what can you tell me? And so what I want to emphasize again is that some of you really do have this skill mastered, which is great. Some of you have the right answers written down on your page, but you can't do this yet. And if that's the case, then what I'm going to tell you is, like, go figure it out. So Tuesday, I didn't really give people scores for these skills. Today, I'm going to, and if you have it mastered, I'll know. And the way I'm going to know is by having a conversation with you. It's not going to be the kind of thing where you come to me and you're like, will you check me off? Will you give me my 5 on this skill? Because that's not at all a evaluation of a skill. It's going to be a conversation, and it's going to look different for all of you. And part of the reason it's going to look different for all of you is because I think I kind of know what you already can do. And so I'm not looking to find out like information that I don't really know. I'm looking to verify the information that I think is accurate. I think I know which ones of you have this mastered. So if you've really got it mastered, then that means a couple of things. One is, if I throw a moderate curveball at you, you should be able to figure it out. If I ask you something and it's a little bit tricky, you should be able to figure it out. More importantly, if I ask you something really tricky, I'll be able to see in your response that you actually do understand how to do this, even if you end up not being able to make the free body diagram. I'm going to give you something that's so tricky that you can't do it. And then in the process of having our conversation, there's going to be lots of, oh, right, oh, yeah, because the friction could be acting this way, or, oh, yeah, because that force could be bigger than this one, so I guess it could be accelerating. Well, sure, yeah, if it does this, then that's going to have a larger normal force. Those are the kinds of things that I'll hear if you really understand it. And so it may be that I ask you to do something really straightforward, and based on that, I can see that you don't really get it, and I ask you to go do some more work. It may be that I ask you something really, really complicated, and you can't get it, but I can still tell that you have mastered the skill to the degree that I think is appropriate for where you are, in which case you might still get full points, right? Like, mastery of this skill at a 11th, 12th grade high school level is not the same as being flawlessly perfect and being able to do this work all the time without making any mistakes. Those are kind of 2 different ways of evaluating. So just be aware that that's going to be happening today. I'm going to be like talking to you and asking you to do stuff, and it's not just going to be show me what you've got for this. It's going to be, here's this scenario, what would the free body diagram look like? Here's this other scenario, what would the free body diagram look like? For some of you, I'm gonna just say, you come up with something. Come up with something really complicated, and then let's talk about it. It's not even like going to be something that I present to you because you should be able to. All right, so that's where we're headed with this. For the homework, there's we've got a few different steps to go through, so bear with me here. Let's start with me just solving question 22. Now, some of you might have accidentally looked at problem 22, and that's fine. It's not like there's grades for this or anything, but when I assign homework, I say whether it's a question or a problem, and I tell you what page it's on. So in this case, this is question 22 on page 167, and our setup is drawn out for us. It looks like this. We've got one block on a ramp, and then there's a pulley and a line and another block hanging off the end of the ramp. And the question is, so here's what we know. We know that it's at rest. So the velocity of the entire system is 0 and stays 0. Nothing's moving, which means there must be no acceleration as well. And the question is, what is the direction of the static friction force on block 1? So there's a couple ways that we could go about this. The simplest way to go about this is to just think about the free body diagram for the forces acting on block 1. So this kind of goes back to, we make a drawing, we establish a frame of reference, just like at the work that you're doing with the lab, just like the examples that I've given you in class. It's always the same. We always do the same thing. So for this block number 1, I know there's going to be some forces that are parallel and perpendicular to the ramp. I also know that there's at least one force, the force of gravity, that isn't aligned with the ramp. If there was going to be motion, it would be in the direction of the ramp. So I know if there's friction, it's going to be in the direction of the ramp. There's a bunch of different ways to do this. But what makes the most sense to me is to use this frame of reference. I'm going to use an angled frame of reference. I'm going to look at the box's motion, all the forces in this parallel dimension, separately from its motion and all these forces in the perpendicular dimension. So let's draw a free body diagram for the box and see where we get. So here's my box number 1. I know there's a force from the string. There's tension in the string. How do you know that? Well, I mean, you don't really have to be told to know that since there's going to be a pulling force down on block number 2, and there's going to be some gravitational force on block number 1, they're kind of like pulling against each other, so to speak. So they're creating tension. They're both pulling on the string. So we know there's going to be tension in the string. We don't know how much. And we know that there is going to be a normal force acting on the box. How do we know this? At the end of Tuesday's class, we kind of went through, like, how do you know? And one of the things that you look for is, well, how would this object be moving if there weren't a normal force here? And the answer is, if we look at all the other forces that would be acting on this object, there's going to be a gravitational force straight down. And then friction, we don't know. We don't know what direction friction is acting. It's either going to be down the ramp or up the ramp. But either way, you can see, like, this object can't be at rest with just these two forces acting on it, nor can it be at rest with these two forces plus friction. Because no matter which direction friction is, there's going to be part of this weight that's not balanced out. So if there isn't another force acting on this, then it's going to be accelerating. Maybe this way, or maybe this way, or maybe this way. We don't know, but we're not going to be able to eliminate this downward acceleration unless we have some sort of normal force. So we know it's there. And then the other piece to this is, what about friction? So let's look at what our possibilities are, right? So possibility one is that there is no friction. Is that possible in this case? We'll see. We'll look and we'll see. Possibility two is that the force of friction is up the ramp. In other words, this box, if there were no friction, would start to slide down the ramp. And possibility three is that the force of friction is in the opposite direction. So we can actually test that. We can test that, and I'm gonna test it in a way that's really like kind of arbitrary, right? So what I'm gonna do is I'm gonna just sort of show you how this could look and how this could play out and how we might test it, just so you can see that all three of these possibilities are real. So what I'm gonna do is I'm gonna take this this little cart and I'm gonna put it on the track. And it's not gonna go anywhere when it's up there. And the reason that it's not gonna go anywhere, we all know, is because there's friction. It's pretty clear that if there were no friction, this thing would go down the ramp. But the beauty of this particular track is that I can kind of turn friction off. So if I turn friction off, let's see what happens. And just fair warning, it's not like ear-splittingly loud, but it's like a vacuum cleaner level volume. So just be aware when I switch this on, it's gonna be noisy. All right, let's see what we get. Oh, oh my, physics. And so we know now that if there had been no friction all along, that this thing would have slid down the ramp. But here's something that's kind of interesting. If I pull on this a little bit, and I've got a little rubber band here so I can pull. If I pull on this a little bit, we can play around with this in some slightly different ways. So one way that I can do this is I can pull on this in such a way that, that without changing anything, if I turn friction off, this cart will now go up the ramp. So it's not moving now, right? It's not moving. You guys sit down. Sorry. It's not moving, but as soon as I turn friction off, it started, you see that? It started moving up the ramp. That's because I was pulling on it. I was pulling on it with just a little bit of force. Not enough to make it move when there was friction, but I was pulling on it with enough force to cause it to move up the ramp when I turned friction off. So what does that tell us? The friction must have been in the opposite direction of my motion. Friction always opposes motion or potential motion. So now we know sometimes friction is up the ramp, sometimes friction is down the ramp. And can we make it zero? Yeah, we can make it zero too. If I pull on this just hard enough so that it doesn't go anywhere, when I turn friction off, then my tension force was exactly enough to balance out the gravitational component that was pulling this thing down the ramp. So these are our three possibilities, and all three of them are like theoretically possible. We don't know which of those is the case, okay? So let's think about this now in terms of what's going on with the tension acting on this object right here, okay? Here's what we know. We know that this object is motionless. If this object is motionless, then we know that the upward force of tension, Ethan, anything? The upward force of tension and the downward force from the Earth's gravitational field have to be equal and opposite. Okay? So what that means is the tension in this string is determined entirely by the weight of that second object. Whatever the weight of that object is going to be the tension. That's true in this case because the sum of the forces on this object is zero since the acceleration is zero. If that's the case, then this upward force and this downward force have to be the same magnitude. There's no other way that we could achieve no acceleration here. So what does that mean? That means that this tension is equal to the weight of our second object in this particular case, because there's no motion, there's no acceleration. And you all know that when we have an object on a ramp, you can take it to the bank, that these two components are what we're going to use for the gravitational force. Whatever the angle of the ramp is, there's going to be a perpendicular component that's equal to the weight of this object times the cosine of the angle of the ramp. There's going to be a parallel component times the sine of the angle on the ramp. And when I apply Newton's second law here, what I get is the sum of the forces in the x dimension are going to equal 0 because there's no motion at all. That means there's no acceleration for either of these objects. So that means all my forces in this x dimension have to add up to 0. Okay? So I'm going to show you a little trick, and it's going to turn out that this breaks our conventions just a little bit. But you'll see in a second that it's a useful trick under these circumstances. So let's say, we don't know, maybe the force of friction is 0, maybe the force of friction is up the ramp, maybe it's down the ramp. Let's pick one of those. Let's say that we're going to assume that the force of friction is down the ramp. With this frame of reference, what that means is the tension is in the positive direction, so that's equal in this case to the weight of the second object. The gravitational force is in the negative direction, and the force of friction is also in the negative direction. Those all have to sum to 0 in order for this object to remain at rest with no acceleration. If I solve this equation for the force of friction, what I get is the force of friction is going to be equal in magnitude to the weight of the second object minus the parallel component of the gravitational force acting on the first object. What determines the weight of the second object? Its mass. Could that mass be really, 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 really small? Yeah. Could it be really, 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 really big? Yeah, we don't know. What determines the weight of the first object? Its mass. Could that be really small? Could it be really big? Yeah. The way this drawing shows up in the book, it looks like object 2 is smaller than object 1, but they're trying to trick you because we don't know what these things are made of. Object 1 might be made of styrofoam, and object 2 might be made of lead. Their size does not tell us their mass, which means their size gives us no information about their weight. So either of these could be heavier. And what about the angle of the ramp? Well, I mean, it looks like it's about 30 degrees in the book, but I mean, we don't have the actual angle. Realistically, if we were going to say like, okay, we got to take the book at its word at some point. Realistically, we could say it's between 25 and 30 degrees. But could you imagine a scenario in which the difference between 25 and 30 degrees is the difference between this block sliding up, this block sliding down, or this block remaining motionless in the absence of friction? Yeah, you can, because you could do that, right? Like we could put, with this lower ramp that I have here, we could put an object on here, hang a weight off the end, and then like kind of balance it, right? I could lift this up and get it so that it was perfectly balanced. Or I could lower it a little bit and it would start to accelerate this way. Or I could raise it a little bit and it would start to accelerate the other way. But we don't know exactly where that angle is. What does that mean? That means that this whole quantity is unknown. This could be a big positive quantity or a small positive quantity. It could be a big negative quantity or a small negative quantity. It could be zero. In this case, our convention of assuming that all forces are positive breaks because we don't know the direction of the force of friction. In this case, when the force of friction is our unknown, it could be in either direction or it could be zero. If you tell me the masses that are involved and you tell me the angle that's involved, I can tell you whether friction is in the positive direction, in the negative direction, or it's zero. But until you give me that information, I can't solve this problem. So the answer to question 22 is D. There's not enough information to tell. And this is really kind of similar to what we're doing in some ways, right? Like we've got in the lab that we're doing right now, where your goals are to work with free body diagrams, to use static and kinetic friction along with Newton's second law, it's really close to this particular situation, isn't it? Which means some of you are thinking, aha, this is a giveaway, right? I just told you what the free body diagrams look like for our lab, and I just told you how to use static, in this case friction, with Newton's second law with regards to our lab. But there's a couple of things that I want you to recognize. The first is that in this case, we're talking about static friction. And remember, the rules of static friction are a little bit different. Static friction isn't a constant amount. There's a maximum, but it can vary up to that maximum. The other thing, and the more important thing, is that in the lab that we're doing, this assumption right here, that we have no acceleration, is not true. This assumption is not true. Oops. It's not true for our lab. There is friction, but it's kinetic friction, and the acceleration is not zero. So the take home for this particular problem with regards to our lab is that while there are some similarities here, this is not the identical situation, which means this work that I just did may or may not directly apply to our lab. Some of it will, and some of it is going to be a little bit different, or maybe a lot different. Okay? And of equal importance to you right now is that while this superficially looks similar to the next question that was in the homework, it's actually, there's some big differences between the two problems that I assigned to you as well. So if you think about problem number 83 on page 174, our initial setup is really similar. We have an object, it's on a ramp, there's a pulley, the two objects are connected by a string, but there's some differences here. One difference is that we know more information. So the object on the ramp is 10 kilograms, the object hanging off the edge is 5 kilograms, and the angle of the ramp is 40 degrees. So we have a bunch of information that we didn't know before. Another difference is that the ramp itself is a frictionless surface. So we could think about, like, that doesn't exist, but sort of, right? Is that completely frictionless? No, but it's pretty close. A supercar on a ramp, is that completely frictionless? No, but it's actually really close to frictionless. So it's not totally unrealistic. And then the other thing that's different here is we are told that there is going to be some acceleration. And in fact, that's the point. That's what you're trying to find. Okay? So, I have no interest, no intention in making you nervous or uncomfortable. So please understand why I'm gonna ask you to do this right now, is because I want you to see what you personally, individually know. So what I'm gonna ask you to do is, without freaking out, without worrying about how this is gonna affect your grade or your score or anything, I want you to put everything away, get out one sheet of paper, a pencil, you can use a calculator if you need it, if you wanna use your phone, that's fine, but don't use anything else. Get up and move away from your support system. So the people, if you are sitting next to somebody that you normally would talk to in doing this work, get up, move somewhere else, and then solve this problem. But I just. For those of you who don't remember,